It's a pleasure to have you, Panayotis, at our seminar. And Panayotis is a principal researcher in the French National Center for Scientific Research and also affiliated with the University of Athens, Department of Mathematics there. So, and today I think he will be speaking about training models with the min-max loss landscape. So I think it will be some very interesting theory in front of us. So Panayotis, the floor is yours. Please start.
All right, Maxim, thank you very much. Thank you very much for inviting me. It is a real pleasure giving this talk and speaking here in this extremely nice and prestigious online seminar. So yes, indeed, I want the idea is to present some recent results and some recent theoretical results regarding stochastic approximation techniques whenever we have problems in machine learning with the min-max loss landscape. And this is actually going to be an overview of several different results that we've gotten over the last few years with several colleagues from EPFL and Grenoble and Columbia. And the starting point, in a sense, is quite far removed from today's era of machine learning. And it goes all the way back to the theory of stochastic approximation and the Robbins-Monroe algorithm, which started back in the 50s as a method for finding roots of nonlinear systems that involve unknown or very complicated functions that can only be accessed by noisy evaluations. All right. And it was at that time in 1951 that Robbins-Monroe essentially developed the SGD algorithm that we're using even today and started analyzing it for the first time, basically at the same in the same time as Kiefer and Wolfowitz, who did some parallel developments on what we would call today zeroth order methods, because they only involve calls of the function to be minimized and not its gradients. But anyway, this is just for historical context for the beginnings of the theory of stochastic approximation. If we fast forward to today, where we wanted to apply this theory and the phenomena that we wanted to understand comes again in ML to systems like generative adversarial networks, GANs, where you have I guess you're all familiar with this, but if you're not, you have a pair of deep neural nets, one generative, another discriminating, and the generator is generating samples from some distribution that the generating is trying to learn, and the discriminating is comparing with true samples from this distribution and is saying whether it is a fake or not. And through this training back and forth, the GAN is ultimately able to produce very good samples from this unknown distribution. What does this have to do with stochastic approximation? Well, in order to train this model, one essentially has to solve a min-max problem where the discriminator is trying to maximize the log likelihood of getting true positives and true negatives, while at the same time the generator is trying to minimize this the performance of the discriminator based on this log likelihood. All right. So in many regards, training such a deep learning system, training a GAN, is exactly equivalent to solving a min-max problem, which in turn has to do which is where essentially the method of the stochastic approximation methodologies will come into play. All right. So I would say that this is the very basic background and motivation for the rest of the talk. The main obstacle that we are encountering in this in this regime is that the functions that we are dealing with are very extremely far from being convex and well behaved. I mean, in optimization, we know we have a very good handle of how to handle or convex objectives and their cousins, weakly convex, star convex, something convex, anyway, problems with a certain degree of a convex structure. But when we are faced with deep learning models, the loss landscape can be extremely complicated. As you see here, this is just a two-dimensional projection of a DNN, of a deep neural network. And what's more is that not only looking for a global optimum in this landscape is an extremely hard and an NP hard problem. When we are dealing with a saddle point problem, with a min-max problem, then in that case, every shift from one network or the other causes basically a tectonic earthquake in this landscape, can change it completely. So even looking for critical points, for saddle points in this framework can be extremely hard. And essentially, this is the main question that we were trying to attack, to see what is the what can be expected from the long run behavior of first order training methods in this context, and to compare, to establish a comparison, a baseline with a comparison baseline with minimization problems, to see if at least certain questions admit similar answers, or if there are some fundamental differences, some fundamental obstacles that cannot be overcome. And if so, what are they, and what is their impact? So the rest of the talk will actually consist of two parts. After a first introduction to set some notation and to define some preliminaries, if you wish, I want to first go quickly through some theory for minimization problems from a stochastic approximation viewpoint, and to examine the long run behavior of first order training methods in a minimization context. And then the second part and the last part of the talk will have to do exactly with min-max problems. What is different? What difficulties we face there? And what can be done. All right. So just to begin, let me set some preliminaries. So the standard minimization problem is we're given a function and we want to find its minimum. The saddle point equivalent is we have a function of two sets of variables, x1 and x2. These are both vector variables, and we want to find a point which is simultaneously a minimum with respect to x1 and a maximum with respect to x2. And in our case, these functions, f of x and f of x1, x2, are actually going to be stochastic, so expectations of random functions, because this is what we have in typical machine learning problems. We have huge finite sums coming from an empirical risk minimization or log likelihood maximization problem. So in all cases, these functions will only be accessible through some stochastic oracle. All right. Whoops, that's a mistake. And yeah, the main difficulties that we're going to face here are, as I said, that the problem has no convex structure whatsoever. We will not be assuming any, will not be making any convexity assumptions. And the function f itself is going to be quite difficult to manipulate in closed form. So exact calculations of gradients are going to be quite hard. I will present some results about the deterministic case where we have full gradient information, but it is really the stochastic case that interests us the most in this talk. And also, just to avoid dealing with an impossible problem, I want to concentrate on a much easier problem. First of all, to see whether it is possible and under what conditions it is possible to find at least critical points, meaning points where either the gradient is 0 or the corresponding min-max gradient of the function is 0. So these are critical points, not necessarily always desirable. These critical points, for instance, in the case of minimization, could include saddle points or even maxima, and we would like to see whether we avoid such points. This will be an important part of the talk, but this is at least what we want to concentrate on, to see whether we get some satisfying convergence theory for critical points, or we encounter problems there as well. All right. So these are the basics for the problem setup. In terms of some blanket assumptions that I'm going to be using throughout, some are structural, some are more technical, some of these can be relaxed. I don't want to give the version of the result with the less stringent assumptions. I want to concentrate on those that will make the presentation simpler. So we're only going to concentrate on finite dimensional Euclidean spaces, no constraints. We're going to assume that our problem does always admit a solution, at least a critical point in either the minimization or the min-max case, and some regularity for the objective, namely Lipschitz continuity and Lipschitz smoothness. Again, we can start relaxing assumptions here and there, but this is a comfortable set of assumptions to work with, so I'm gonna make them throughout, and I'm not going to keep mentioning them. And what else? Yes, I should also discuss the general class of algorithms that we will be looking at. And in general, we will be working with a very abstract stochastic approximation template of this form. So what this means is that the state of the algorithm is being updated modulo by taking a step along a stochastic approximation, as it is being said, of the problem's defining vector field at the point in question. So this could be either the gradient of the function to be minimized or the min-max gradient of the min-max objective correspondingly, either of the two. And this gamma n over here is a step size. So just like SGD in a sense. We will explain the differences with SGD and why this is a considerably more general template. But first of all, in terms of the step size, the assumptions that we'll be making is that it is of the form gamma over n to some power. So the exponent could be anything between 0 and 1. And what is more important is the stochastic approximation here, what we label the stochastic approximation of g of xn. So this could include not only some zero mean noise, all right, but also a certain offset, all right, a certain bias, which one way of looking at it is that this bias, this offset, is some sort of systematic error of your gradient oracle. But we will see below, and I will show some concrete examples, that this offset could actually be used to model an extensive range of algorithms other than standard gradient descent. All right, so let me go right into presenting some examples. The most basic example here, and I will just be presenting in the figures the corresponding minimization profile, just because the min-max profile is very hard to draw. The standard gradient descent ascent algorithm, here again showing just the descent, is that we are at a certain point, we evaluate the gradient, we take a step along the gradient, and this is what generates us the new gradient. All right, if we have full gradients, the algorithm is deterministic, and of course there is no offset. The algorithm is run with true gradients. All right, now a variation of this is the so-called proximal point method, also related to the proximal gradient method, which is the following method. So instead of taking the gradient at the starting point and taking a step along it, along this direction. The proximal point method assumes that you can somehow calculate the gradient at the point that you will end up in, and you are taking a step along this direction. So it is, of course, a theoretical. It is a theoretical method. It is not something which is implementable in practice, because in order to perform an update, you need to be able to solve a nonlinear system of equations, which is in general not any easier than the original problem at hand. So this is a conceptual method, but still a very useful conceptual method, and one which has very good convergence, theoretical convergence properties, and which has been studied extensively in the literature, starting all the way back from the 70s. And what is important is that this implicit gradient update, this proximal point update, is, of course, deterministic, but it can be captured as a stochastic approximation just by noting that that the gradient that we're taking a step along is not so much different than the gradient at the starting point. And if we compare the two, the difference between them is of the order of the step size of the method. So we can really consider this as a special case of the general template that I presented, with no noise and an offset which is of the order of the step size of the method. All right. An implementable approximation of this method is the so-called extra gradient method, which is extremely popular for solving min-max problems and variational inequalities. And the way it works is that you start at a point, you take a step at, you take a standard gradient step, and you generate a leading state, an interim state, if you want, an intermediate state. And then what you do is you take a gradient, you evaluate the gradient at this intermediate point, and you update an algorithm by taking this gradient and taking a step from the leading point. All right, and this is your update of the algorithm. So you start at the base state, you generate this interim state, you calculate the gradient at the interim state, and this is your gradient update. And again, this is a deterministic method, which can be captured as a special case of this general template with an offset, which is again of the order of the step size. Now, this method has the drawback. This is a very good approximation of the proximal point method, and it has superior convergence properties to ordinary gradient methods in a min-max context, but it requires two gradient calls per iterations, because we need one gradient here and one gradient here in order to perform the final update. All right, there is a variant of this method, which is called the optimistic gradient method, and which dates back to Popov in the 80s, and it was rediscovered essentially by Rachlin and Sridharan in the early 2010s. And what it does is, instead of taking a gradient step, what it does, it is essentially reusing the last gradient observed to perform the first intermediate step, and then it proceeds just like the extra gradient method and generates this new update, this new state. So again, this is it is called optimistic because we are reusing past gradient information to do this first update, and we hope that everything will be okay. And again, this is still a special case of the method because all the gradients involved differ from the original gradient by a factor which is of the order of gamma n, where gamma n is the step size of the method. All right, now all this was with perfect gradients. You can imagine that I can run all these algorithms, gradient, extra gradient, optimistic gradient, with stochastic gradients. What does a stochastic gradient mean? It means that we do not have access to g of x at any given point, but at some random approximation thereof, which on expectation gives us the right gradient, and let's say it has finite variance, to simplify things. All right, so we can imagine rerunning all this spectrum of algorithms just with stochastic gradients. So this is how we would be obtaining stochastic gradient descent, which was the original Robbins-Monroe algorithm of the 50s in their 1950s paper. We have stochastic extra gradient, stochastic optimistic gradient, etc., etc., etc. All right. I can go on and on about the type of methods that we can include in this very general framework. Perhaps the only honorable mention, which is qualitatively different than the rest, is the Kiefer-Wolfowitz approach, which what it does, this is a zeroth order method because it does not assume any access to the gradients. What it does is it is picking a random direction here or here, completely at random, and then samples the function at one step up, one step down, divides by the corresponding finite difference width, and essentially constructs an estimate of the gradient based on function observations alone. All right, and this method is a stochastic method because the direction is picked at random, and also it has an offset because the estimate of the gradient is not perfect. It has an O of delta n error relative to the true gradient, where delta n is the width of the finite of this finite difference quotient, and but otherwise it is just a special case of this stochastic approximation template. So what we're going to do is we want to use this framework because if we get results for this general framework, they are going to simultaneously apply to all these algorithms. So we don't have to do an ad hoc analysis for each algorithm. We don't have to write 3 pages of proof for each algorithm. We wanted to derive a sort of a general theory covering all these algorithms at the same time. And the main idea of the stochastic approximation method is that if we go back to the definition, well, essentially what we see is that on average, it is just like, it is as if we are taking a discretization of a differential equation. All right, so what we can see, this very general stochastic approximation update as sort of a discrete version of these continuous dynamics, mean dynamics. And so the idea is that if we are somehow able to make this link precise, to link the discrete time method with the continuous time method, and we are able to analyze the trajectories of the continuous time method, then we will directly have results for the discrete time method. And this is essentially the basic idea that we're trying to leverage, that if the step size sequence is small enough, then the errors that we're performing in this stochastic approximation must somehow wash out, become negligible over time, and the limit of the discrete time process would somehow, in some sense, to be defined, coincide with the limit of the continuous time process. All right. So this is what I'm going to try to make a bit more precise in the rest of the talk. And I will start with some applications to ordinary minimization problems just to set the pace. Here things are relatively easy because we have a gradient flow. What does a gradient flow imply? It implies that the function to be minimized is what is known in dynamical systems as a Lyapunov function. and which means that the trajectories of this flow will decrease this the objective function in value, and unless we are at a critical point. So this is a very good property, a very strong property to have. And it is thanks to this property that we can get some very strong convergence results for this entire range of algorithms. All right. We need some technical assumptions to do this. The first technical assumption is a structural one and concerns the function G, the vector field G. It is what we call subcoercivity, which basically means that it does not, that the vector field does not point towards infinity. All right. That, you know, outside some arbitrarily big compact set, it is not pointing outwards. All right. That's the subcoercivity assumption, which concerns the vector field or the function here to be minimized. And in terms of more technical assumptions, we also need some requirements for the step size of the method and the bias and noise parameters. All right. So the big result, the main result here is that if we have these sometimes called Robbins-Monroe or Kiefer-Wolfowitz summability assumptions, then with probability 1, the sequence of iterates generated by any of the stochastic approximation algorithms will converge to a component of critical points of the function to be minimized. This was originally proved by Bertsekas and Tsitiklis in 2000 for SGD, for stochastic gradient descent, and then with Nadav Halak, Ali Kavis, and Bolgan Gerer, we extended the proof to the entire range of stochastic approximation algorithms in Europe's paper in 2020. All right, so this is a first convergence result, which tells us that at least in minimization problems, the trajectories of all these methods, even with stochastic gradients, will converge to a component of critical points. All right, so this is good news. But at the same time, if we have a complicated non-convex landscape, we could also have entire manifolds of undesirable solutions, like Ridge manifolds here, meaning a manifold of maximum points, or also saddle points, etc., etc. And of course, not all these points are desirable from a minimization perspective. We would like to be able to say with certainty that we are not getting trapped in this type of traps, in this type of saddle points, in this type of non-desirable spurious critical points. And here, the first, at least to my knowledge, result, the first avoidance result of this kind was obtained by P. Mantle in the 90s, and then there was a follow-up by Brandière and Duflo, who focused on what is known as hyperbolic saddle points. What are these? They are isolated critical points, which are saddle points in the sense that the Hessian of the objective function has at least one negative eigenvalue. All right. And hyperbolicity means that the Hessian itself is invertible. So they are generic in this sense. Now, what this means is that hyperbolicity means that the flow, the gradient flow, is linearly unstable near this point. So convergence to such a point would be highly unlikely. Now, this intuitively is very, well, not surprising. It is expected in a sense. However, it is incredibly difficult to prove. And it relied on some very difficult probabilistic estimates that P. Mantle first derived, and then, as I said, there was a follow-up by Brandière and Duflo in the mid-90s. And it also relies on what is known as a uniform excitability condition for the noise, which means that it has a non-zero component along all directions. There are no directions where the noise is zero. All right, I'm not saying it's isotropic, which means that it would be the same along all directions, but it has a non-zero component along every direction. So what P-Mantle showed is that if there is no offset in the algorithm, so we're talking about SGD basically, and the noise is uniformly bounded and uniformly exciting, and we use a 1/n step size, which was extremely popular back in the 90s up to the early 80s, but now it is extremely unpopular because it can be quite slow in practice. But anyway, under these assumptions, the probability that we will end up converging to a hyperbolic saddle point is 0. So there are some assumptions, of course, but the end result is extremely strong. All right. So this was the basic result, in a sense, for a lot of time. We need to fast forward around 25 years to get to a different type of theory for non-hyperbolic saddle points known as strict saddle points. The strict saddle points maintain the assumption that the minimum of the eigenvalues of the Hessian is negative. So there's at least one negative eigenvalue there, one unstable direction in a sense, but there is no invertibility assumption for the Hessian. All right, so they may be non-generic points. And here it was Ronguet and co-authors that provided the first avoidance result, which is quite different, both in spirit and in terms of mathematics from the result of P-Mantle. Because what they said is, give us a tolerance level. This tolerance level will be for a high probability bound in the sense that the end result will hold with probability at least 1 minus this tolerance level. All right. And okay, let's take some assumptions for F, which are what we currently have. A bit more regularity, so they need a Lipschitz continuous Hessian, but that is not a big deal. What is perhaps a bit more tricky is that we require some sort of trichotomy in the various points of F. So the various points of F must either have sufficiently large gradients, or they must have a sufficiently unstable eigenvalue in the Hessian, or they must be sufficiently close to a point around which F is strongly convex. All right. So these are so this is a certain class of functions for which these are certain structural assumptions that are needed in order for the theory to work. And then we need some more assumptions which are comparable to P-Mantle. So no bias, again, it is SGD. And then the noise must be uniformly bound and contain some uniformly sampled noise. So there is an injection of noise in the algorithm. And finally, the step size is taken constant and equal to basically to be of the order of 1 over log 1 over z, where zeta is this tolerance level. All right. Under all these assumptions, what Gay et al. Showed is that with probability at least 1 more minus zeta, if we run the algorithm for 1 over gamma squared times basically log of 1 over gamma zeta iterations, it will produce a point which is square root of gamma close to one of these locally strong local minimizers of F. and since it will be close to this point, and since we have this trichotomy, it means that it will have to be far from any strict saddle point. All right, so basically with high probability, after we run the algorithm for sufficiently long, and with a suitably chosen step size, the algorithm will produce an iterate which is close to one of the local minimizers of these locally strongly convex minimizers, these second order minimum points of F. All right. So as you can see, I mean, this is why I was saying that it is different in both spirit and of course the mathematics involved to prove it. What we wanted to do is to see if we can somehow bridge the gap between P. Mantle and Gay et al. And provide an almost sure result, which is for strict saddle points, but not necessarily for just either with high probability or with a specially tuned step size or having this trichotomy for the functions. And it turns out that it is possible to do so. And what we also managed to do, this was in our paper with Nadav Halak and again Ali and Polka in Europe's 2020, was that if we have an offset term, which is sufficiently big to cover the various extra gradient, optimistic gradient algorithms that I talked about before, and the noise satisfies the same assumption as in P Mantle, and we take any step size with any vanishing step size of the form 1 over n to the p, then we can show that the probability that xn converges to a set of strict saddle points is precisely 0. So with probability 1, we avoid all strict saddle points or manifolds there. All right. So this is basically the baseline for minimization problems. And in a sense, all the stochastic approximation or Roberts-Monroe methods converge to the problem's critical sets, and they avoid spurious, non-minimizing critical manifolds. All right, this is the general gist of what we can obtain in a minimization context. And what we wanted to see is whether these type of results also extend to min-max optimization problems. So specifically, whether we can get convergence to unilaterally stable stationary points, critical points in a sense, and whether we can avoid points that are not min-max points. All right. The main difficulty here, of course, is that in contrast to minimization problems, the gradient flow in a min-max problem is not a gradient flow. It is a Hamiltonian flow, but still it can be arbitrarily complicated. All right, precisely because we don't have a potential structure. Nevertheless, if we start with the second question here, there is a powerful result that can be obtained for avoidance of non-min-max point. And the result is that if we have the same assumptions for the offset and the noise of the algorithm as we have in the minimization case, then the probability that xn converges to an unstable point, so meaning a point where which is not a local min-max, so the probability that it converges to an unstable point is 0. All right. And you can also extend this to more general periodic orbits that may arise in min-max settings. But for now, forget this part. The important thing to keep in mind is that even in a min-max setting, the probability of converging to an unstable, to a non-local min-max point is 0. So these would be very good news, because we can somehow say that this was the difficult perhaps part from the minimization part, so we should be in the clear. Unfortunately, the problem is that min-max problems that the first part, which would be the easiest part, the easier part, the base part in the minimization context, can actually give us a lot of problems in a min-max context. And specifically, if we have a non-gradient problem, we could have entire attracting sets, not points, but sets that have no critical points, but they are still attracting. All right. And so I'll start by giving some examples of this type of result by focusing on a very, very simple bilinear problem. All right. So you can even forget the matrix. You can just take f of x1, x2 to be simply x1, x2. The simplest bilinear problem imaginable. All right. If you take this problem and you look at the corresponding flow of the mean dynamics, then what you have is basically a foliation of periodic orbits. All right. Now, what you can show in this system, and this is what we showed with Christos Papadimitriou and Yoros Spurious, is that this flow in any bilinear min-max problem is what is known as Poincare recurrent, which means that every continuous trajectory will come infinitely close to its starting point infinitely often. What does this mean? It means that if the stochastic trajectories, if the discrete time trajectories are approximation of this flow, then we cannot expect convergence. And indeed, this is what we can also observe in practice, that even if we run stochastic gradient, stochastic extra gradient, whatever, what happens is that both extra gradient, optimistic gradients with stochastic feedback, they all converge. I mean, there is some noise involved, but eventually they converge to one of these periodic orbits. All right, it will be random based on how the noise evolves and the initialization, but they will all converge to this periodic orbit. There are, specifically for the case of bilinear problems, or merely monotone problems, there are some very specific tweaks and fixes that we can do in order to improve this, but only in the case of bilinear or merely monotone problems. This was a work by Tatiana Chavdarova in 2019, and again another work with my student Yuguan Shi in NeurIPS 2020. But again, these two results that I am citing here concern bilinear problems. Beyond bilinear problems, we have an issue. What is this issue? Well, I'm going to skip this more technical slide because these concerns the fact that bilinear problems are in the range of min-max problems. They are somehow very rare. The behavior that we see in bilinear problems is not at all typical of general non-convex, non-concave problems. All right, this the justification of this relates to a twin theorem by Kupka and Smale, which is a very deep theorem in dynamical systems. But I don't want to expand too much on this. I'll be very happy to discuss this in the question part later. What I want to focus on is what happens when, instead of having a portrait like that, where we have these foliation of periodic orbits, none of which is attracting. All right. What do I mean by the fact that none of which is attracting? It means that if I focus, for instance, on this periodic orbit, then if I start at a nearby point, no matter how close, I will never converge to this periodic orbit. So it is not attracting. It is stable in the sense that if I start near this orbit, I will not drift very far away from it, but it is not attracting. All right. So the first thing we wanted to study is what happens to attracting sets. All right, sets of a min-max dynamical system which are attracting. And what we showed, whoops, I'm sorry, you shouldn't be seeing this. I'm sorry about that. What we showed is that if we have an attractor of this mean dynamical flow, of this mean flow, I'm sorry, and we have these stochastic approximation step size conditions, these are basically regularity conditions, technical conditions, then what we showed is that this attractor is what is known as stochastically asymptotically stable. What does this mean in layman's terms? It means that you pick a probability threshold, then with probability arbitrarily close to 1, if I start close enough, I will converge to this attractor with at least this probability. All right, this is what stochastic asymptotic stability means. And this was the result that we got with Yaping Shi and Volkan in ICML 21, and which initially made us very happy because this was, it told us that if we have a set which is attracting under the mean dynamics, under the continuous time dynamics, then this set will be also attracting for the entire range of algorithms that we've been considering. So we were very happy precisely because these attractors were exactly the sets of critical points in the minimization context. The problem that we realized early on was that in the min-max case, there are spurious such attractors. There are attractors like that which are traps, which do not contain any critical point whatsoever. And unfortunately, they are embarrassingly simple to construct. So you take the original bilinear game, which again is very simple, it's the simplest min-max game that you can imagine. And what you can do is you can simply perturb the function of only the second player, of the max player. All right, and you perturb it by a very small amount with a very simple polynomial function. All right. When you do this, then for any level of perturbation, this almost bilinear game has a unique critical point at the origin. This is the only critical point of the game, but it is unstable under the mean dynamics, and the only stable set under these mean dynamics is exactly a limit cycle which is around this critical point. So what the image looks like is that you have this almost bilinear game, and instead of having these periodic orbits around it, what happens is that all trajectories will start escaping this critical point, the unique critical point of the game, and all outside algorithms will, all outside initial conditions will start spiraling in, and everything will be captured in this limit cycle, in this spurious attractor. And this is not something that you can escape with any of the stochastic approximation methods that we discussed. Proximal point, stochastic gradient, stochastic extra gradient, stochastic optimistic gradient, whatever. All these methods will end up converging on this limit cycle, no matter what you do. And in fact, you can have even the case where not only is the center point a critical point, but it could be the unique Nash equilibrium of the game. All right. And well, this just takes a slightly more complicated perturbation of the game to achieve. But what happens is that when you perturb this, it loses a bit of the min-max, it loses the min-max property, and it is now trapped by two attractors. One of them, the inner attractor, is unstable. The other outside attractor is stable. So what happens is that in this case, the original solution point of the game has a basin of attraction which can be arbitrarily small and which can be escaped with arbitrarily high probability. And once this basin of attraction is escaped, then everything is again trapped by this spurious limit cycle, even though you're starting with a strong equilibrium in the middle. So, in a sense, this is the main gist and the main message that I wanted to convey. That minimization and min-max problems in the non-monotone, in the non-convex, non-concave regime are fundamentally different. Even though in the convex or in the monotone regime, they have a lot of similarities, and we have a very well-established convergence theory for problems with a convex structure, whether they be minimization or min-max problems. When we go to a non-convex, when we lose any semblance of a convex structure, the story is completely different. Even if we have avoidance of unstable points in both cases, the attractors in minimization and min-max points are completely different. And in the min-max case, we have attractors that are spurious and thus attract, even though they do not contain any critical point whatsoever, they attract all first order stochastic approximations, all zeroth order, and even some second order stochastic approximations. So the open questions, there are many, is whether we can somehow do better by going beyond the first order case and do some more intelligent second order method. There's a recent paper by Daskalakis and co-author who has some first encouraging result in this direction. And whether we can do better in at least cases which are non-convex, non-concave, but at least have more structure, like finite games. And to try and study there which equilibria are stable under first order or regularized learning methods and all that. But yeah, this is perhaps a story for another time. So I see it's the hour is almost up, so I'll stop here, and I will be very happy to take any questions you might have.
Panayotis, thanks a lot. It was extremely interesting, and probably colleagues will have some questions. They unfortunately can't speak, but they can write. While they're writing, I probably will start with one or two questions myself. So I'm not an expert at all in this min-max problems, but currently the classical optimization problems they seem to be studied extremely extensively, like from all the different directions, and first order, second order methods. Even recently third order methods came up, some from Nesterov and so on. And here I'm curious, so you mentioned that some work on second order methods started. Do you mean some deep analysis, or even they just started developing the methods which are suitable? So
let me try to answer. You finished the question. I didn't interrupt. Okay. So yeah, in our paper with Yaping and Volkan, here, this one, we actually studied some second order methods, some simple second order methods, because there are several. And it turns out that they're basically variants of adaptations, rather, of Newton methods to a min-max context. All right.
Okay.
So in that case, you can show, we showed that the flow of this method actually also exhibits these spurious attractors. So precisely because we had the convergence theory, the general convergence theorem that any stochastic approximation will converge to the attractors of the mean flow, then this allows us to get directly traps for this class of second order methods. But depending on the preconditioner that you use, if you do not use a Newton method, or if you use, as you suggested, perhaps a third order method or something else, there things can be different. Now, I would suspect that it might be hard. I suspect that these spurious attractors are somehow ubiquitous in the sense that even in third order methods or higher order methods, they are still present, even though they might be more difficult to construct. But yeah, at what extent going to higher order methods will help escaping this type of attractors, it is not clear. It is not clear.
Okay, that sounds very interesting, and it's sort of exciting for me that for relatively simple formulations, still a lot of things which are unknown. So it seems to be a lot of work for you, your colleagues, and future guys doing this topic.
And you, I hope.
Probably yes, and well, and we have actually.
Yes.
Yeah,
Okay, I see.
we have a question. So
Yes.
let me read it for the audience. So for stochastic gradient descent with constant step size applied to neural networks, there is a phenomenon that after a very long time, the algorithm reaches a stationary regime with some fixed value of time averaged loss. For smaller step sizes, this value is lower. So the nature of critical points around which the algorithm spends most of its time in stationary regime is different for different step sizes. Can this be characterized theoretically?
Very, very deep and very difficult question. So, short answer is I'm not familiar of such a characterization. I will tell you what the closest thing that I can to a reply to this. What you can there is some theory for certain very specific neural network models, which tells you that that essentially all global all local minimizers will be concentrated along will exhibit an exponential concentration around the global minimum and around the zero loss, the zero empirical loss surface. And there is an adjoining theory that tells you that the probability of landing outside this this exponential basing grows with the step size. So this would be somehow consistent with what you're describing, though of course it is in no way a full answer to this question. A more precise characterization of the attractor basing on of SGD based on the method step size. This is, yeah, I'm not. This is very difficult. I'm not familiar of any satisfactory theoretical response other than what I said, which I realize is not fully satisfactory, but that's the best I have.
Okay, that means that we have another open question, and
yeah, for sure.
Yeah, and actually, I think Maxim, who asked this question, another Maxim, he has many similar questions around the theory of deep learning, because he's working a lot with this convergence regimes, different different laws which happen there. All right, so actually I don't see more questions from the audience, and probably it means that people might have future questions and they probably can write you, I suppose.
Absolutely, it would be a pleasure.
Yeah, that's great. And then I want to thank you for this very interesting talk and for opening for us this part of optimization theory. It was amazing, and hope to see you some other time with some new results.
Thank you so much. Thanks a lot for having me. It was a pleasure being with you guys.